Hello everyone, welcome to the video on linear interpolation and skew for S1. What we're going to do is, we know how to find the median and quartiles for discrete data, i.e. if we have like 4, 5, 6, 11, 13 or whatever, we would normally take the n over 2 value, wouldn't we? In this case there's 5 values. So that's 5 over 2, it will be the 2.5th value, and we would round up to make that the third value. So therefore Q2, the third value, is 6, so our middle value. This time though, what we've got is continuous data in the form of the table at the top left-hand side of the page. Now if we've got continuous data, we don't have to, because we want an exact answer really, because continuous data, remember, can be decimals, it can be any point. And therefore, we don't need to round up or round down or go halfway between two numbers, whatever. We can just say it is that number, the number that we're actually looking for. So for continuous data, we do not round up or go halfway between two values for a start. Now, because what we have here is essentially a histogram, so frequency density versus our weight here, which has been put in terms of kilograms, and they've been rounded to the next nearest kilogram. What we have is this step, 40, 50, and then 51. So at the moment, this is not a continuous table. This histogram here can't be represented by this table at the moment. So first off, we need to change our classes to 39.5 to 50.5 and 50.5 to 80.5 and 80.5 to 120.5 and 120.5 to 140.5, and our frequencies don't change. Now what we've got to bear in mind is that when we had a bunch of numbers or a frequency table before without this grouping, we could kind of allot, couldn't we, like which numbers had that exact frequency. But we don't know where these three numbers, where this frequency of 3 came in this class, or rather this class. Like, did those three come between 39.5 and 42.5, let's say, or did they come between 42.5 and 43.5? We don't know. So all we can do is assume that everything is equally spaced. So each bar is has an equal proportion of the frequency inside it, okay? So in other words, for this 10, we're assuming that those 10 frequencies have been equally spaced between each class. So I should have the equivalent of 10 strips in there, really. Alright, so we're going to operate on that premise to try and find the median Q2. So if we've got this median Q2, first off we need to locate the nth over second value. Well, there's an easier way to do it if we include another column called the cumulative frequency, which means we add them up as we go along, because we're looking for, well, how many are there for a start? Well, let's do the cumulative frequency then. So I've got 3 here, and then in total, so far I'm going to have 13, 3 plus 10, and then I'm going to plus the 17, so that makes 30. And then I'm going to add my 5, which gives me a total of 35. So there are 35 over 2th value, which is our 17.5th value, is our Q2 number. Now where does the 17.5th value lie? Well, this class here finishes at 13. This class here finishes at 30. So 17.5 must lie somewhere within this class. Remember, we assume that everything is equally spaced. What would a systematic way, if this is our 80.5 to 120.5, somewhere in here, and remember all our frequencies are contained within here, somewhere in here is this 17.5th value. Where is it? Well, what we can do is we could look at that bar in a different way. We could look at this bar by saying, well, the class starts at 80.5 and it finishes at 120.5. Q2, our median value, must lie somewhere within that bracket. So on here we've got our class. On the bottom we've got our frequency. So the frequency on that class started at 13 and it ended on 30. So again, that Q2 value, that 17.5th value, must lie between 13 and 30. As they're equally spaced, what we're saying is that this proportion, Q2 subtract 80.5, must... So Q2 subtract 80.5 is a fraction of this 120.5 over 80.5. So what I'm saying is that from 13 to 17.5, this is a certain amount of the entire bar here, isn't it? Likewise, then, this 17.5 minus 13 must be the same proportion as 30 minus 13. So what I'm saying is that this fraction must be the same as this fraction here. The proportion where Q2 lies in the class width must be the same as the proportion where that frequency, the 17.5th value, the 17.5th frequency value must lie between 13 and 13. So what we're saying is that Q2 subtract 80.5 all over 120.5 minus 80.5 must be the same as 17.5 minus 13 over 30 minus 13. If we rearrange everything then, we get Q2 equals, and now we can start timing up. So 120.5 minus 40.5, 80.5, sorry, is 40. So there's our 40 lots of 17.5 minus, I'll just write that in, 13 over 30 minus 13. And then you've got the plus 80.5 here, which is this bit here. So all I've done is times up by there and then put that over the other side. And what you end up then is Q2 is 91.0884 if you use your calculator. So we're saying that Q2 is 91.1 to 3SF. And that makes sense really, doesn't it? That 91.1 would lie kind of in the middle of all this data because 17.5 is going to lie somewhere near the front of this class, because remember this class is worth 40, so evenly distributed. Yeah, I'd say that sounds about right. You can do Q1 and Q3 in exactly the same way, n over 4 and 3n over 4th, but don't round up or don't go between that and the nearest whole number, remember, not for continuous data. And I think that's enough for linear interpolation there. Now we're going to talk about skew. Right, so skew is always something that kind of intuitively, I think even teachers have trouble as well kind of remembering what skew is. It positive, negative, or symmetrical, and this kind of thing. And I think this all comes down to, well, what do we really understand by what skew means? So let's start this off from the beginning. Let's imagine we have a load of discrete data. So it doesn't have to be discrete, it can be continuous, but either way, let's say we have a frequency density diagram like this, and this is for discrete data, or continuous even. Imagine if I had a histogram, right? Let's look at it that way. Let's look at a histogram. So we've got continuous data here, and I'm trying to make this on my picture look virtually symmetrical. So this is a symmetrical histogram. If I want to make this is continuous, isn't it? If I want to make this like curved, so a smooth bell shape like this, what do I have to do? Well, I just have to keep reducing my, I have to make my bars equally spaced, so my class widths need to be equally spaced, and I need to make them so small that essentially there are just an infinite number of lines, and then you notice that their endpoints are going to be dots. So if I shade this all in, we now have a fully continuous curve representing our histogram. But it doesn't matter. It doesn't matter if I use the curve or non-curve. This is just for illustration. So what we're saying here is that this has zero skew. This is symmetrical. Okay? So we're starting off with symmetrical data, and well, where does that kind of come in? And this links nicely with the normal distribution function. This looks exactly like normal distribution function. So if we were talking about heights in college, if you get enough people, the data would be symmetrical. You'd think that the majority of the data, the frequency density in the center, the average height would be the highest. You would get the highest frequency there. And then in the extremities, kind of the shorter people and the taller people would kind of even out with each other in terms of frequency number. So it makes sense that we have a zero skew or something if we're talking about heights. Now let's imagine that suddenly the New York, the LA Lakers come in, or the Chicago Bulls come in. They're bringing their entire team into our college, and then we took a sample of everyone's height then. Well, in that case, what's going to happen is, because there's so few of them, but yet they're so tall, notice that if we did our frequency density graph now, we'd still get a mode. We'd still get a mode in the center, because notice here that our mode is in the middle. Remember, that's our modal value, where our frequency density is highest, is in the middle. So is our mean going to be in the middle, because remember I said the extremities even out. And our median, our middle value, makes sense that it's obviously in the middle. But what's going to happen when the LA Lakers walk in, because they're so tall, they're going to have so few of them in these categories, but because they're so tall, it's going to extend the data towards the right, isn't it? And notice what's happened then. The mode, the majority of us in college are still going to be a certain height, and that's not really going to change. The median, though, is going to shift slightly to the right, because the median is the middle value and there are more people now, so it's still going to be slightly more to the right. And also our mean average is going to be pushed to the right. It's going to be skewed in the direction of the right. So it's going to be skewed in the direction of the positive axis. So this is positive skew, you see? Positive skew when the mode is less than the median, which is less than the mean. Similarly, if we had a bunch of primary school kids coming into our college, so they'd obviously be much shorter, they are extending our data to the left, towards the negative side. So they are skewing our data negatively. So we've still got our mode, which is our, the majority of us are in a certain class width. Our median's going to be pushed to the left, because there's more data this time, so we've still got the middle value here. And our mean's going to be pushed to the left as well. It's going to be skewed towards the left, towards the tail end. So we've got negative skew. So what we're saying is that now the mode is bigger than the median, which is bigger than the mean. A really good way that Stella thinks about how to remember the direction of skew is this idea of, she will hope to remind me saying, so she uses that idea of this hump like we've done before, this positive one here. She's saying if you're a skier, if you start up here, if you're a skier on the mode, are you going to have a positive time or a negative time? Well, you're going to have a positive time. You're going to have a great time going down that slope, okay? So if the hump of the mode is on the left, you're going to have a great time, because your median and mean and stuff is going to be to the right of it. Whereas if you were starting on the left here, you'd have to climb up this hill, and therefore if you're a skier, you're going to have a negative time. You're going to have a horrible time. You're not going to be going anywhere, okay? So there we go. In terms of our graphs, we can tell what kind of skew we have here, okay? Box plots, how can we tell from box plots? Well, box plots, very, very similar. This time, I've got a box plot, this is symmetrical, 2 M's, i.e. Q2 is directly in the middle between Q1 and Q3, okay, it's directly in the middle, and everything's evenly distributed. And so what we're saying is that if we were to subtract Q3 and Q2, this would be exactly the same as subtracting Q2 and Q1. Whereas, in our example of the Elliott Lakers, etc. coming in, if they were skewing all our data to the right, so they're much taller, notice that we have positive skew here, because in my box plot, I still have a Q2 and Q1 relatively close together, but Q3, because my data is being pushed outwards to the right, again, another maths teacher, Mark, has a great analogy for it. He's saying that if you were to hold a piece of paper, positive skew on a box plot would be to stretch out your paper towards the right-hand side. So a box plot means you have a larger gap between Q3 and Q2 than you do between Q2 and Q1. So this is positive skew. Likewise, if I had the primary school kids coming in, Q1, Q2, Q3, our paper would be stretched towards the negative side. So we're saying in that case that our distance Q2 minus Q1 would be bigger than Q3 minus Q2. And there we go, that's skew and linear interpolation in one video, and we're happy. There is another degree of skew where you can, it involves a formula involving the mean and the standard deviation, but we can look at that another time, I think. And that just gives you a number between 1 and -1 to give you a degree, very similar to correlation, regression, etc. But we can talk about that another time.